This is the Unit 15 practice exam. First here we've got a multiple choice section, so make sure that you're familiar with these concepts. And some of these are actually sort of rigorous, so study your notes, come and ask me if you have any questions, just make sure that you really understand all of these questions. And so the first one here says, according to the collision theory of chemical reactions, what effect do you think decreasing the volume of gases would have on the rate of the reaction, assuming that the number of moles of particles and the temperature remain the same? So this requires that you know the collision theory of chemical reactions, which says that in order for a chemical reaction to happen, a collision has to occur between the particles of the reactants in the chemical equation. And then what happens is they reach this transition state. In order to reach that transition state, the collision needs to have enough energy. And so in this, what we're going to do is, say there are two ways that a chemical reaction can be sped up. One way is by having more collisions. The other way is by having higher energy collisions. And so thinking about what would happen here, if we took a gas and we took its particles and we condensed it down into a smaller volume, we're putting those particles in closer proximity to one another. That means that there's going to be more collisions, all right? Which means that the rate of the reaction is going to increase. Looking over here at this picture, so what this is it's a picture showing the energy involved in these different reactions. So this is in one of your sets of notes in the equilibrium notes, so make sure that you're familiar with this. What happens is C here represents the reactants. The energy has to go up so that it can reach this transition state. So the transition state is kind of this high energy point. And then in this case, this is an exothermic reaction because the products end up having less energy than the reactants do, so they end up releasing energy to the environment. But what happens is the reactants hit each other, it bounces up to the transition state, and then it falls back down there to the products. And so that transition state is that high point of energy there. So this says which one of these represents the activation energy of when a catalyst is being used. Well, there are two different activation energies. All right, one of them is going from here up to here. That's where the reactants start, up to the transition state. That's the less stable transition state, and so it takes a lot of energy. The smaller transition state is just going from the reactants up here to that smaller hump. And what's happening here is the catalyst actually makes the transition state more stable, which means you don't need as much energy for the reaction to happen, and so collisions don't have to be as strong. And so a catalyst increases the rate of a reaction by decreasing the amount of energy needed there. And so in this case, the amount of activation energy for a catalyst is represented by letter E. Which following one word best defines equilibrium? I've talked about this a number of times in class, so hopefully you know that it is balance. So that one is B. This next one, it says, what does it mean if KeQ of a reaction is greater than 1? So there are 6 things on your review that you should sort of be familiar with. If KeQ is greater than 1, what it means is that it is product favored. Okay? The equilibrium is product favored, meaning there are more products than there are reactants at equilibrium. Now, if you look at this, none of these say that, and so D is the correct answer. To interpret what these different things are here, when the reaction proceeds left or right, it wouldn't be at equilibrium. So in this case, we're actually talking about Q's. So if the reaction proceeds left, that means it's going towards the side of the reactants, which means that Q is going to be greater than KeQ. So it needs to go left to make less of the products, more of the reactants. If it's going to proceed right, that means Q is less than KeQ. All right, the reaction being at equilibrium, that means Q equals KeQ. So these are all talking about Q, which is the reaction quotient. It's not talking about KeQ. And so the correct answer on this one is none of these. Number 5, it says, what does it mean if Q for a reaction is equal to 1? So looking up at those 3 above, we actually, Q, you have to know what the definition of Q is. KeQ is the equilibrium constant. It's the ratio between products and reactants at equilibrium. Q is a test to see if we're at equilibrium or not. You figure out what Q means by comparing it to KeQ. Because I haven't provided you with a KeQ in this problem, there's nothing that you can do with that Q. So E is the correct answer. All right. So if a reaction is at equilibrium, that means Q equals KeQ. But again, because we don't know what KeQ is for this one, we can't do that one. The reaction is product favored. This means KeQ is greater than 1. If it's reactant favored, that means KeQ is a decimal or it's less than 1. All right, the reaction is neither product nor reactant favored. Okay, that is KeQ equal to 1. So know what these KeQs and Qs mean, and what the definition is, and how to interpret them in these different situations, because this will surely show up on the actual exam. Number 6 and 7 are talking about concepts with Le Chatelier's principle. So this is considering the following reaction. What effect would result from removing SO3 gas? So if we're taking away this SO3 gas, what we're doing is we're removing a reactant. Le Chatelier's principle says that it's going to react by trying to undo whatever change we're making. So it's going to try and produce more of that reactant. If it's trying to make more of that reactant, it's going to shift to the left. So that is A. For B, it says, according to the same reaction, what would be the effect of increasing temperature? If you're increasing temperature, you're adding heat. All right. If you're adding heat, then it's going to try and shift to the side of the reaction that doesn't have heat on it. This one's endothermic. You can see that heat is shown here by saying that there are kilojoules on this side. And so if it's going to shift to the side of the reaction without heat on it, it's going to be shifting to the right side of the equation. If we had reduced the temperature, it would be shifting to the left side. All right. So that is B. Section B here is on problems, and so you have to know how to do different calculations with these. The first one here is a KeQ problem. It asks you to calculate KeQ. That's products over reactants. The coefficients become exponents. So we start here with SO3 squared over SO2 squared times O2 to the first because it has a coefficient of 1. Plugging in numbers here, we get 0.88 squared over 1.6 squared times 0.4. If that's the case, we multiply those together, we get 0.756. All right, so this is the correct KeQ. This is less than 1, which means that it is reactant favored, but it didn't ask us that in this case. Okay, so number 9, at equilibrium is the following reaction product favored or reactant favored given that CO2 is 0.75 and CO is 1.8. So notice here that they don't include the carbon. It's because carbon is solid, and so if something is solid or liquid, it's left out of the KeQ equation. If there's only solids or liquids on the product side or the reactant side, include a 1 as a placeholder. So because it's products over reactants, for instance, let's say that we had only a solid on the product side, well, then we would have 1 over whatever the reactants are. That way, you still have the sort of ratio that you typically have, and you can still perform the calculation. So in this one, KeQ equals products over reactants, leaving out the carbon. We get CO squared over concentration of CO2, which gives us 1.8 squared over 0.75. You calculate that, and you should get 4.32. This one is greater than 1, so KeQ here is greater than 1, which means that it is product favored. For question 10, we have to find Q because it's asking us if the reaction is at equilibrium or not, and if it's not at equilibrium, it's asking us what direction the reaction is going to proceed. So we have to calculate Q. Q equals the same thing. It's the same sort of calculation as KeQ. So you do products over reactants. The difference is here we're not necessarily at equilibrium, whereas when you're plugging numbers in for KeQ, the assumption is you are at equilibrium. So here we get NO3 squared over NO2 squared times concentration of O2 to the first. So it has a coefficient of 1. All right, so plugging numbers in there, we get 0.42 squared over 0.15 squared times 0.25. Calculate that out, you get 31.36. Okay, and then this is the payoff here. We're comparing Q to KeQ. In this case, KeQ is 27.5. And so we see here that Q is greater than KeQ. If that's the case, that means we have too many products, not enough reactants. So the reaction is going to proceed to the left, which is A. For the throwback here, it's good to just go through the throwback worksheet and make sure that you're understanding this. But what we have here is we've got in number 11, there is just one product here. If there's just one product, that indicates that you're talking about a synthesis reaction. So that is A. For the next one here, what we've got is we've got this hydrocarbon and oxygen. It produces carbon dioxide and water. You should identify there that that is a combustion reaction, which is E. Okay, remember, if you have any questions on this, try and come in and talk to me, preferably before the day of the test, just to get yourself sorted out and so that you have some extra time to study.